Namaste and welcome to this course on mathematical foundations for machine learning. This is Dr. Arulalan and I will be starting the lecture series for this particular course. The first week of this particular course is focused on vectors, vector spaces and subspaces. So, this is again going to be a kind of holistic course like what we had last in our linear algebra through geometry course. So, what we are trying to do is we are going to give a holistic picture of all the ideas and concepts of linear algebra, probability, statistics, calculus and optimization as applied in machine learning. So, what we do is we get into the idea of vectors and then we will see like what are the operations that are done on vectors and what is a vector space, and then we look at what are the subspaces of a vector space, like how do we combine vectors first of all. So, what is the combination of what does a combination of vectors result in, and we will look at a whole lot of interesting stuff and we will also look at it from the perspective of machine learning. So, we will try to talk the language of machine learning as much as possible as far as this course is concerned. So, on that note let us get on to the idea of vectors and vector spaces. So, what is this vectors all about? Now, all of us we would have at some point of time we would have seen that vectors are nothing but in our school definition vectors are something with let us say magnitude and direction. This is what quantities with magnitude and direction, this is what we would have been taught. And what we are going to do is we are probably trying to come out of this and then get a very abstract definition for the vectors and let us see like how just it is not about the vectors with which you denote with a line segment and an arrowhead which is indicating the direction. It is not about that, it is much more deeper and profound than what we actually had studied in high school or probably in the first few semesters of our college education. So, what we will do is we will look at vectors like what do we mean by vectors. So, first of all let us write down what are we going to do in this module. We are going to look at vectors, this will be the module content. We are going to have vectors, vector spaces and vector space and subspaces, vector subspaces, that will be the focus of week 1, right. So, great. So, what is a vector? So, let us look at what a vector is, and the idea of vectors like how do we actually construct vectors. So, all those things we will just check in the course of this lecture. So, what is a vector? We say that okay for example let us start with this. Let us say I say that a vector, I define this vector u to be let us say a 2 component vector. I am going to define this as a 2 component vector. We are going to say that a vector u has, this is a 2 component vector where you have let us say 2 component vector with the components being u1 and u2, with components being let us say u1 and u2. Now, what does that mean? We have all studied that in let us say in the 2 dimensional plane. So, suppose I am going to have something like this, I have my let us say x1 axis and I have my x2 axis. Now, what we do is let us mark some arbitrary points. So, let us take this. So, suppose I say u is this vector which is like say 2 comma 3, let us say u is this vector which is let us say 2 comma 3. Now, what does this mean? This vector u has 2 components along the x axis and it takes a value 3 along the y axis. So, the vector is going to be this is our primitive idea of vectors. I am going to say u is equal to 2 comma 3, right. So, it is basically I mean when I say it is a 2 component vector, it is basically a couple of numbers which could be real, which could be complex or whatever. So, what we do is we try to focus more on real valued vectors. We will take real vectors where the components are basically real numbers. So, let us do this. So, what we are going to do is we are going to say u is a real vector in the sense that the components of this vector are basically real numbers. So, the components are real numbers. Real numbers, right. So, how do we construct this vector? So, I can do this, I can also take this u to be let us say u1, u2 etc., let us say un. I am going to call this as an n vector, or probably I am going to call this as an n component vector where the components are going to be real numbers, n component vectors. That means you are going to have an ordered n tuple. So, this is going to be an ordered n tuple. Right. So, what do we mean by all these things? I have ordered set of numbers. So, what? So, what does this actually mean? This could, what does this imply, like what could it mean? It depends on the context. Say for example, I can take this, I can take the I can look at this. So, I will say that suppose we let us say measure the let us say the body parameters of a person, of a patient, let us say biological parameters of a patient parameters. These let us say these n components could be the n different. So, this n components could be n different parameters that people actually measure. So, n components indicate the n parameters that we measure. We measure, for example, you can say u1 could be the let us say the blood pressure number of a person, blood pressure. Let us say u2 could be let us say the blood glucose level. u3 could be let us say pulse rate. u4 could be let us say heart rate, and u5 let us take this to be the SpO2 levels. So, what are we going to say? We are going to say that the vector u is basically a 5 component vector which has these parameters u1, u2 to u5. So, this basically is a collection of 5 parameters. Parameters as mentioned above, right. Now, what we do is when we collect data, typically we will collect these 5 parameters let us say from 100 different patients, and then let us say we take it from 100 different patients. So, what we are going to do is we are going to actually put that across as let us say this. So, I am going to collect these 5 parameters from let us say 100 different patients. So, what are we going to have? 100 different patients. So, I am going to put all these things in a tabular form, and what I am going to have is I am going to have something like this. So, I am going to have P1 to let us say P100. Every person I am going to collect u1 to u5, this is going to be u1, u2, u3, u4, u5. So, I am going to take 5 records I mean record of 5 parameters for each of these patients. So, what I will end up getting is I will actually get a matrix of dimension which is 100 by 5. This is okay. This will basically become my data matrix, where the number of rows is going to indicate the samples or the patients, and each column is going to indicate different parameter that I am going to measure. Right now, I mean this is like fine from the application perspective, but mathematically how do we get these vectors? So, what we do is we look at a very fundamental structure to the idea of vector space, what we call as say we call this as our field. We have a mathematical structure which we call as the field F. So, what does this do? If I want to get this structure called the vector, I must have something fundamental to the structure which we call as the field, a mathematical structure which we call as the field, right. So, how are we going to define this field, and we are going to look at some examples of field, and then what we do is we are going to see how we are going to generate these vectors, how are we going to construct these vectors. So, that is something which we will see now, and then subsequently we will look at what are the operations that can be done on the vectors, as mean what are the operations that are there defined on the field, and what are the operations that are defined that can be defined on the vectors, and so on. We will see it in subsequent lectures. So, what is a field? A field is going to be a non-empty collection of elements. See, it is a non-empty collection of elements with let us say with operations, let us say plus and dot. I am going to put these two are these binary operations that I am going to have, that they are going to have two operations that you have. One is called the field addition, this plus is called field addition, and this I will call this as field multiplication. Field multiplication operation. So, I am going to call this as these two operations are going to be defined on this non-empty collection of elements with operations such that the following properties hold. The following properties hold. So, what are the properties that we are going to look at? Let us see the properties. The first property that we want to look at is the following. We say that there exists zero in the field such that for any element A in the field, A plus 0 is equal to 0 plus A is equal to A. Then the second property is for any two elements A comma B in the field, for any two elements, let us say A comma B in the field, A plus B is also an element of the field, right. So, if you take two numbers from the non-empty collection, you add them, the resultant is also going to be an element of the field. Then we are going to say that there exists for every element A in the field the additive inverse minus A in the field such that A plus minus A gives me the 0 element. So, it basically gives me 0 and then so this 0 basically whatever we have written a plus 0 is equal to a, this 0 is basically called your additive identity element, additive identity, right. And then what we have is we are going to look at some more, then we are going to take this fourth property where we say that there exists the element 1 such that there exists element 1 in the field such that a into 1 is equal to 1 into a is equal to a. Then we are going to call this by some name, we are going to say that 1 is called the multiplicative identity element, multiplicative identity. Then we have the fifth one for a and b in the field, we are going to say a into b is also an element of the field. And the most important property of the field is that for every non-zero element, for every non-zero element a in the field, there exists a unique element A inverse such that I mean there exists a unique element A inverse in the field, let us write that, in the field such that A into A inverse is equal to A inverse into A is equal to 1, and we are going to give a name for this A inverse. A in the we are going to give a name for this number, this entity A inverse. This is called the multiplicative inverse of A, multiplicative inverse of A, right. So, it says that for every non-zero element that you have in the field, there is a unique A inverse such that A into A inverse is equal to 1, that is the multiplicative identity element, and A inverse is called the multiplicative inverse of A. Now, if in fact if you have all these 6 properties to be obeyed by a set, then you call that set as your field, especially with those 2 operations plus and multiplication, you call this entire set as a field. So, let us take some examples and see like what it is to say a field. So, let us consider this first example. So, consider the set of real numbers, consider the set of real numbers R. So, the first thing that we want to check is whether this real number set has 0. Of course, we know that 0 is a real number, it is an element of R. Then we know that for any 2 real numbers, if you add any 2 real numbers a comma b real, the sum of 2 real numbers is always real, this is what we get. So, this is an element of R. Then we have among the set of real numbers, we have for every a in R, we have a negative a in R such that a plus minus a is equal to minus a plus a, which is equal to 0. That means existence of additive inverse is there. I mean the additive inverse for every element A exists, and then we are going to look at this. We know that 1 is a real number. So, 1 belongs to R, that means multiplicative identity element is there. Then we have the fifth one, for every A B in R, that means 2 real numbers, the product of 2 real numbers is basically a real number, that is what this means. A into B is also a real number. And the sixth one, for every A not equal to 0, we just check if I made that for every non-zero element. Okay. So, for every A not equal to 0, we have and A element of R, A real number, we have A inverse such that A inverse into A is equal to A into A inverse, which is equal to 1. So, if you take the number 2, the inverse of this is basically half, and half is also a real number. So, the product of half and 2, you basically get the number 1, which means existence of additive multiplicative inverse, right. So, there is a, for every non-zero element you also see the multiplicative inverse to exist, and therefore, you say that the set of real numbers is basically a field. Therefore, R is a field, R is a field over with operations, let us say with operations real addition and multiplication, right. So, this is an example of a field. Of course, complex numbers you will see it is a field and so on. But what is interesting is, let us take the simple case. What is a case that we want to do? We will take up this example 2. I am going to look at set of integers. Set of integers. Now, we know that 0 is an integer, and let us say this belongs to this set. Let us call this as let me call this as, let us say n. So, it is basically an element of this n. Then for every A and B in n, I am going to have A plus B to be an element of n. For that means, if you add any two integers, the resultant is going to be an integer. So, that is guaranteed. Then we are going to have this for every A an integer. We can always find a negative integer minus A in n such that A plus minus A is equal to 0, this is there, and then what we have is 1 is an integer. So, we have the fifth property which says 1 is an integer, fifth or fourth property. So, this is the fourth property that we have. One is an integer. So, we have that 1 into A is equal to A into 1, which is equal to A for every A in n. The fifth one, you take any two integers, the product of two integers is going to be another integer. So, I am going to say A dot B is A into B is basically an integer for any two integers A comma B. Right. But all these 5 properties work with the set of integers. The property that fails is basically this. Suppose A is an integer, suppose A is an element of, let us say n, for example, let us say for example A is equal to 2. Then what is A inverse? A inverse is basically half, the multiplicative inverse, it is half, and this does not belong to n. Therefore, what we see is set of integers is not a field. So, you have set of real numbers to be a field, but set of integers to be not a field. It's a bit disheartening because integers are nice to work with. I mean, rather than real number multiplication and stuff, integers can be easily multiplied, added, all the operations on integers seems to be pretty simple. And now what we see is we find the set of integers to be wanting in the sense of a multiplicative inverse. That multiplicative inverse of integers need not be integer. Therefore, the set of integers fail to be a field. Now what do we do? Is there a way in which we can probably make the set of integers a field, because integers are nice to work with, right. So, can we do something to make the set of integers a field? Let us try this out. Consider this, let us take this example. Consider the set of integers, consider the set of integers, let us say modulo 5. Now what are we going to look at when we say modulo 5? We are not going to do anything great, we are just going to look at the set of remainders when you divide by 5, the set of remainders that we get when we divide by 5. When divided by 5, right, we want to look at this. So, what are the numbers that we can get when we divide by 5 as remainders? So, let me call this set as R5, right. I am going to look at R5, which means I am going to look at set of remainders or set of integers that you will get when you divide by 5. So, what does this set contain? This set R5 contains these elements 0, 1, 2, 3 and 4, right. You will see that when you divide any number by 5, either the number is a multiple of 5 or the number leaves a remainder when you divide by 5, or 2 when you divide by 5, or 3 divided when you divide by 5, or 4 when divided by 5, right. So, I am going to just look at this. Now, what I am going to do is I am going to define my operation plus in such a way that I add the numbers, whatever numbers that I have, I add the numbers and then I take modulo 5. This means addition modulo 5, I add modulo 5. That means you add the two numbers and then take the remainder of the sum when you divide by 5. I am going to define this plus this multiplication as multiplication modulo 5. This is interpreted as multiply modulo 5, right. I am going to put this as multiplication mod 5. So, let us see what happens with this. So, let us look at what we wanted to see. We want to check whether from the set R5, if you take any two elements and then add and then do a mod 5, the resultant must be an element of the set. So, what I will do is I will just draw a table and then see if we are able to put all these operations in a table and try to understand it using the table. So, what I will do is I will do this. So, I am going to write all those 5 numbers that I had 0, 1, 2, 3 and then 4. So, let me do this and I am going to do the same business here. Let me write it 0, 1, 2, 3 and 4, and the operation that I am going to do is basically mod 5 here. So, if I add 0 and 0 and do a mod 5, I get 0, and this is going to be, you are just going to add the number with 0. So, I am going to get 0, 1, 2, 3, 4, and this I am going to get as 1, 1 plus 1 is 2, 2 mod 5, 2 when you divide by 5 you get remainder 2, 3 when you divide by 5 you get remainder 3, 4 when you divide by 5 get remainder 4, and 5 when you divide by 5 you are going to get a remainder 0. So, you can easily fill the rest of the table. So, 2 plus 0 mod 5 is 2, 2 plus 1 mod 5 is 3, 2 plus 2 4 mod is 4 mod 5, which is 4, 2 plus 3 is 5, 5 when you divide by 5 you get remainder 4, 2 plus 4 is basically 6, and 6 mod 5 we know it is 1, then I have 3, 4, 0, 1, 3 plus 3 is 6, 6 mod 5 is 1, 3 plus 4 is 7, 7 mod 5 is 2, and so you get 4. The next element we are going to look at is 4, 4 plus 0 is 4, 4 plus 1 is 5 mod 5 which is 0, 6 mod 5 which is 1, 7 mod 5 which is 2, and 8 mod 5 which is 3. Something interesting that we see here. What we see that if you take element from R5 and add with any other element with R5 in R5 and then do a modulo 5, we end up getting elements which are in the set R5 itself. All these numbers inside the table that you see are all, so these numbers are all elements of R5 itself, right. So, these numbers are elements of R5 itself. That means, R5 we are going to say is going to be closed under addition modulo 5, addition mod 5. So, do we have does 0 belong to R5? Yes, of course 0 is there, therefore, the first property of the field holds good. So, you have the 0 element. Then we want to check if the addition of 2 elements of the field is going to give another element back in the field, especially when you do mod 5. That is what we have seen. We have the very idea of calling it to be closed under addition, field addition basically says that any element, any 2 elements you take from R5 and then add and do a mod 5, the resultant is going to be an element of the set R5 itself, and that is what we see in this table. But I want to check whether there is going to be an additive inverse for every element. Do we have additive inverse? What do we mean by additive inverse? You take a number and you must add a number to that number. Say for example, I have a number A, I need to add a negative A to it so that I get 0, right. Now, I see something interesting happening here. If you look at across the diagonal here, all these elements are 0 and of course, this guy is also 0, that is 0 plus 0. Now, what it says is something interesting. It says 1 plus 4 mod 5 is 0, and how did we define the additive inverse? Additive inverse is that number which when you add to a given number A, the resultant must be 0. Therefore, we see that 1 and 4 seem to be the additive inverse of each other, because if you add 1 to 4 and do a mod 5 you get 0, and you add a 4 to 1 and do a mod 5 you get 0. So, I have this, so I have this element of R5 and then I am going to write the additive inverse element of R5 and the corresponding additive inverse I am going to write now, additive inverse of those elements that I have in R5. So, I have 0, 1, 2, 3 and 4, and for 0 when you add 0 to it you get 0, for 1 you do additive inverse, I will do mod 5, that is more important. So, I take 1 for that element 1, if I add 4 I get 5, 5 mod 5 is 0. For 2 I take the element 3, 2 plus 3 is 5 mod 5, 2 plus 3 is 5 and then I do a mod 5. So, 5 mod 5 is 0, 3 I add 2 to it, so I get 0, and 4 I add 1 to it, so I get 0 modulo 5, which means for every element in R5 I actually have an additive inverse. So, that is a very interesting find that I have. So, what do I write? I say that for every element, for every A in R5 we have minus A in R5 minus A in R5. That means additive inverse mod 5 exists for every element in R5. Additive inverse modulo 5 exists for every element in R5. Is this okay? So, this is something interesting that we have. But the problem is not with addition. The problem that we had when we looked at the set of integers was non-existence of multiplicative inverses barring that element 1. Every other element, when you take every other integer, the multiplicative inverse is going to be a fractional number, which is going to be not an element of this, which is not an element of the set of integers. That is where the problem is. Now we need to check whether this guy that I did with mod 5 is going to allow us a multiplicative inverse for every element in R 5. So what I will do is I will do this multiplication mod 5 and then see if I can check there exists this multiplicative inverse for every fellow in R 5. Because multiplicative inverse is defined only for non-zero elements, so what I will do is I will just take 4 columns here, marking them as 1, 2, 3, 4. I will not consider the element 0 because it does not really matter. So what I do is I will take mod 5, I will take this 1, 2, 3 and 4. I have this 1, 2, 3 and 4. Now what I do is I take the product of this column element with the row element and then do a mod 5. So what do I see here? So 1 multiplied with every element is going to give the same element that you have multiplied with. So I get 1, 2, 3, 4. Then I have 2 into 1 which is 2 mod 5 which is 2, 2 into 4 is 4 mod 5, 2 into 3 is 6, 6 mod 5 is 1, 2 into 4 is 8, 8 mod 5 is 3. Then 3 into 1 is 3 mod 5 which is 3, 3 into 2 is 6, 6 which is like 1 mod 5, and 3 into 3 is 9, 9 when you divide by 5 you get a remainder 4, and 3 into 4 is 12, when you divide by 5 you get a remainder 2. 4 if you multiply with 1 you get 4 mod 5 and then do a mod 5 you get 4, 4 into 2 is 8, 8 mod 5 is 3, 4 into 3 is 12, 12 mod 5 is 2 and 4 into 4 is 16, mod 5 is equal to 1. Something interesting that we see here, what is that? We see that if you take any element from the set R 5 which is the set of remainders that you will get when you divide by 5 and multiply with any other element which is there in R 5 and then do a modulo 5, you do a mod reduction mod 5, the resultant element, the product is always going, the product mod 5 is always going to be an element of R 5, that means R 5 is closed under multiplication. So we say that R 5 is closed under multiplication. R 5 is closed under multiplication. That means I have to see the properties that I had listed for field, I have to see whether that holds. So what is the first property that we had? The fourth property that we checked there was basically saying 1, existence of 1. So is 1 there in R 5? Of course it is there. So 1 is an element of R 5, that means the multiplicative identity element exists modulo 5, multiplicative identity exists mod 5 exists in R 5. The fifth point that we want to say is we want to check, you take any two elements of R 5, multiply and then do modulo 5, the resultant must be an element of R 5. So what we see that you take any two elements, let us say we take this we take element 2 and then we multiply it with 3 and then we get a mod 5 which is 1 which is an element of R 5. You take the element let us say 3 and multiply it with 4, you get the element 2 which is again an element of R 5. Then you take this element 2 and then multiply it with 2, you get this element which is 4 which is an element of R 5. You take 4 and then take this 4 and then multiply it with 2, I get 3 mod 5. That means you see that when you multiply two numbers from R 5 and then do a modulo 5, the resultant element is also from R 5. Therefore what we are going to say is we are going to say that for A comma B in R 5, A modulo 5 multiplication modulo 5 B is also element of R 5. Now the moment of palpitation comes now, because we want to check whether there is going to be multiplicative inverse existing for every non-zero element in R 5. So let us look at that. Now how did we define multiplicative inverse? Multiplicative inverse is simply that element which you multiply with, let us say A in R 5 should give you a 1, right. So, that is what we defined as multiplicative inverse. So, let us probably check if that exists. Let me do this, let me first clear this off. So, look at every column and every row, I find something interesting. There is a 1 here, there is a 1 here, there is a 1 here and there is a 1 here. And how did we get this? We basically multiplied these two guys and then we got a 1 here. We multiplied this guy and that guy and then we got a 1 here. Then we multiplied this guy and this guy, we got a 1 here. And then what we did? We basically multiplied this guy with this guy and we got a 1 here. That means the product of two numbers modulo 5 is giving me a 1, which means one of these numbers that I multiply with is going to be the multiplicative inverse of the other. So, for example, here you take, we see that for every A in R 5 there exists a unique multiplicative inverse. Multiplicative inverse naturally has to be unique. So, I will say a unique integer mod 5 such that A into, let us say, A inverse, let me call this as A inverse mod 5, A into A inverse. So, let me put that in the notation that we had. So, we are going to have A modulo 5, multiplication modulo 5 into A inverse basically gives me 1 mod 5. So, this I will use equivalence relation, this is basically called the congruence, this is called the congruent symbol, right, because you can have multiple numbers which when you divide by 5 can give remainder 1. So, I call this as congruent. So, what I do is if I take for every element we have this. So, what does that mean? I take my elements to be, let us say, I take these elements A is equal to 1, 2, 3 and 4. Now, I am going to check A inverse mod 5, I will write this as A inverse sub 5 indicates that it is mod 5. When I multiply 1 with 1 I get 1 which is the multiplicative of 1 into the inverse of 1 is itself. When I take 2, if I multiply 3 with 2 I get 2 into 3 6, 6 mod 5 is 1. When I take 3 I multiply it with 2, 3 into 2 is 6 mod 5 which is 1. I take 4 I multiply with 4 I get 4 into 4 16 which is 16 mod 5 I get 1. Therefore, we see that what was not possible with the entire set of integers we see that happening here. We see this particular idea of field happening for a smaller set of integers with a specific operation called the modulo 5 operation, addition modulo 5 and multiplication modulo 5. So, when we do that we find this set of these 5 integers 0, 1, 2, 3, 4, 5 forms a field, that is a field. So, what I am going to do is this is very interesting. So, the question, so what we are going to say is the set R 5 is a field with operations addition modulo 5 and multiplication modulo 5, right. So, set R 5 is a field. So, we defined vectors, we saw what is a vector, and in order to build a vector we need a fundamental structure, we call that structure as a field, and we were actually trying to figure out, we defined the properties of field. Now, what we are trying to figure out is what all can be field. We saw that set of real numbers is a field, however, set of integers was not a field, but set of integers modulo 5 is a field. Now, the question that we have is, look, does that mean set of integers mod any integer, let us say n. So, which I am going to call this as R n, these are basically set of integers modulo n. Okay. So, I am going to ask this question, is R n for any n a field? right, where n is an integer. So, this is the question that we have. So, we saw that modulo 5, the set of integers mod phi is a field. So, emboldened by this, we ask a question, is the set of integers modulo any integer going to be a field? That gives us some kind of confidence to look into this. So, what is the answer for this? Can the set of numbers that you get, integers modulo any other integer, let us say n, will that be a field? Will that always be a field? So, what we will do is we will stop with this, we will take the answer for this question. So, we will answer this question, is Rn for any n a field? We will answer this question where Rn is nothing but set of integers modulo n. We will answer this question in the next class. Namaste.